Hi everyone, welcome back. So in the last lecture we discussed transformer, different blocks of a transformer model. Today we will discuss different types of pre-training strategies. Okay, so the prerequisite for this lecture is that, so I'm assuming that you guys are aware of static embeddings coming from what to wake love kind of methods, right? And you're aware of the transformer method and of course RNN CNN. So we will see that from the static embedding or pre-trained embedding, we are now moving towards pre-trained model. So initially in what to wake love kind of methods, we pre-trained the embeddings of words or tokens. Now we'll talk about pre-training an entire model. Okay, and what is the meaning of pre-training? Basically, assigning weights to the parameters. Okay, but before that, breaking news is as follows. So all of you know, I guess, after almost 4 years or 5 years, OpenAI released a new open source model. Okay, and this is called GPT-OS, right? It came with two versions. One is a 120B parameter model, which is on par with O4 mini, right? Which you can basically run on a 80 GB GPU, right? A kind of 1A100 GPU, right? And they also released a small version, a small model, right? It's a 20 billion model, and this is on par with O3 mini, and you can run it on a 16 GB. 16 GB memory is nothing. Okay, you can run it on your mobile also, right? Mobile, or I mean, you should be rich if you if you have a 16 GB mobile, but you can at least run it on your laptop. Okay, it's a good news. And if you look at the blogs, this blog, you see that the performance is really great, right, across reasoning models. And the good part is that now you can use these models for your research if you don't have large GPU access. All right, let's move on to the main part. So we all know about what to wake, right? What vectors, where right, we essentially look at, and these what vectors are context independent vectors. Remember this is context independent vectors. Therefore they are called static embedding. Why static embedding? Because the embedding of a word is independent of the context where it appears. Okay, you can just think of it as a dictionary lookup. Okay, but all of us know that, let's say the word like mouse, right, bank, okay, they have different senses in different contexts, right? So the representation of a word should be context dependent. Okay, so in 2018 there was this paper called ELMO, right, and they came up with in 2018. So you may imagine that transformer came in 2017. In initial days, 2017, 2018, nobody knew about transformer in that way. And the hunch of making bigger models with normal RNNs, right, were still ongoing at that time. And the ELMO method was the first method where they introduced a big model, right, with lots of RNN layers, right, and they came up with a concept called context dependent embedding. Okay, if you want to know more about ELMO, please again look at my previous year's lecture. So and then they also came up with this idea called pre-trained models, right? So they basically pre-train their entire models, right, so that you just need to download their weights and then you can essentially run your applications on top of that. Okay, but during that time, so transformer came before that around the same time, and we have seen two blocks, encoder blocks and decoder blocks, right? Then people saw that in some applications you may need only the encoder block, some applications you may need only the decoder block, and some cases you need both encoder and the decoder blocks. So encoder block is needed where? Encoder block is needed where? Where you basically have access to all the tokens at the same time, right? For example, because encoder block uses non-mask self-attention, remember this. Okay, for example, sentiment analysis, right? You have access movie review analysis, you have the entire movie review and then you analyze the reviews and so on and so forth. Decoder only model is used when your objective is next door prediction. For example, machine translation. Machine translation is not decoder only. Let's say, let's say dialogue setup, right? Where you want the your dialogue agent to generate things one by one, right? You can use decoder. You can also use machine translation, by the way. You can use decoder only model for machine translation. Okay, in a different way, a bit tricky. Whereas encoder-decoder model can be used in any many-to-many sequence-to-sequence models, right? Sequence-to-sequence tasks, MT, summarization, and so on and so forth. We will see later that people realized over the times that encoder model is not a good idea. Encoder-decoder is also not a good idea. So people actually started building only decoder-only models because of many reasons. We'll discuss all these things later. But let us look at now, for the time being, let's look at the encoder-only models and how to pre-train an encoder-only model, right? And the first paper which came out from Google in 2018 is called the famous paper called BERT, B-E-R-T, Pre-training of Deep Bidirectional Transformers for Language Understanding. It's an encoder-only model pre-training. Okay. So how do we pre-train? So for pre-training, the entire pre-training will happen using something called self-supervised learning. Okay, self-supervised learning. What is that? You do not need any labeled data. You do not need any labeled data as such. So in BART, what they said is that, how do we pre-train BART? So BART is only an encoder-only model. Remember, encoder-only model, there are multiple layers and self-attention feed-forward, self-attention feed-forward. So what they said is that let's do something called mask language modeling. Mask language modeling. What is mask language modeling? You are given free-form texts, right? And what you do, you mask some of the tokens, right, from the text, and you let the model predict those masked tokens. So you do not need any label data. Do we need? No, right? You just need the free-form data, free-form text, and you mask some of the tokens, right? And you let the model predict those tokens. What does it mean by letting the model predict those tokens? What is this mask? So what they said is that you mask only 15% of the tokens. 15% is less, very small. You can also increase it, but they showed that 15% is empirically a good number. So your task is to identify 15% of the tokens for masking, right? Now among this 15%, you take 80% of this 15% and you mask it. What does it mean? You introduce a new token called mask. In your vocabulary, you basically add a new token called the mask token, and you also have its corresponding embedding coming from what to wake, for example, or some random initialization. You replace those original tokens by this mask token, right? 80% of time. 10% of time you replace a word by another word, not by mask. So you see here example like going to the park, you replace park by the token mask. Like going to the park, you replace park by store, a random word, right? And remaining 10% time you keep the same token. So if I keep the same token, then why this thing comes under 15% of random masking? No, so then it should not come, right? Because it is basically same as the remaining 85% of sentences. So why then we added this here? Because when we do the prediction for 85% sentences which are not part of our investigation, we will not calculate any error, we will not measure any error. But for this 10% cases, I will also measure the error. You see the difference between the two? Okay. So you identify 10% cases, 15% cases, 80% of them will be replaced by mask, 10% of them will be replaced by other tokens, and 10% of the cases you keep the same token. Mask language modeling, right? And you let the model predict. So how does it work? So this is my input. Okay, so like going to the park to the mask is my input, and I expect my model to predict like going to the park, right? And I calculate the error only here, not here, not here, not here, right? At the position of masking I will calculate the error. And what's the error here? Cross entropy between the actual token, which is park, and the predicted token, which may be lawn or field or store. Okay, and if you pass store here, your expectation is that the model will produce park here. It's a big expectation though, right? And then if you pass, and it may happen that during the process the model may forget to remember the actual token. So therefore, through these examples you force the model remember the actual tokens, right? If the model only learns how to predict mask tokens, if the model only learns how to predict the shuffled or replaced tokens, right, model may forget, the way it should remember the actual tokens, right? Therefore you are saying that look, it is good that you are learning new things, but you should not forget the original one. Okay, all right, so this is the first task for PTS. Okay, so this is easy, this is difficult, right? And this may be even difficult, because over the times the model will try to learn how to predict mask tokens but may forget the original tokens. Okay, so this is the first objective of the pre-training method. There is another objective. The other objective is next sentence prediction. What is it? So in our free form corpus, I know that sentence 1, sentence 2, sentence 3, sentence 4, these are the sentences, right? Sentence 2 follows sentence 1, sentence 3 follows sentence 2, and so on and so forth. So what I will do, I will identify a pair of sentences, right? Let's say SI plus 1, okay, where SI plus 1 follows SI in the document, actually follows SI. I also identify pairs of sentences where it is SI, SJ, where J is is not I plus 1. So Sj doesn't follow Si. So if we have 50% of pairs which are true cases in our case, right, and remaining 50% of pairs which are negative samples, right. So what I'll do, I will pass in the encoder, I'll pass Si, Sj, and so I'll pass like this: Si, then a new token called separator, SEP, okay, and then Sj to the encoder model, and I will ask the model to predict whether Si follows Sj or not. It's a binary classification, yes or no. Okay. Now, why this task is important? This task is important because the first task that I mentioned, mask language modeling, there you are basically asking the model to understand tokens, understand the orientation of tokens within a single sentence. Here you are asking the model to understand, the orientation between two sentences, two sequences. So intra-sentence, inter-sentence. Right now, the interesting part is I will do both objective 1 and objective 2 together during the training time. It is not the case that I will first do objective 1 mask language prediction and then I will do objective 2, which is next sentence prediction. How do we do that? I have only this encoder block, right? How do you do that? So we will do in this way. So let's say I, again, my favorite example, I am going right to mask. Okay, this is my input, separator, mask is far away. Okay, so sequence 1, sequence 2. Okay, I get the embedding of I am going, so these are all pre-trained embeddings. Okay, and then in the encoder block, so this is my first encoder block. All these self attention, feed forward network, all these things will happen, right? And then what I do, I will add another token here, which is called CLS token. CLS stands for classification. CLS is another new token like mask. Okay, so I'll get what, the vector attention with whatever attention vector or some vector for CLS here. Here I'll get a vector for I. Here I'll get a vector for M going, right, mask, separator, and so on and so forth, right? So corresponding to the mask token, I will measure the error. So here and here I will measure the error using cross entropy, right? And corresponding to the CLS token here, what I will do, I will add a task specific layer, which is just a feed forward network, right, which will essentially project it to a 2D space, a distribution over 2D, which is yes or no. This is a task specific head. Okay, so here the model will predict something, yes or no, right? If it is yes, and if it is actually yes, then there is no loss, right? So here the loss is with respect to next sentence prediction task, and here the losses are with respect to the mask language modeling objective, and both these losses will be back propagated end to end. Now my question is, why do I need a CLS token? Can't I just concatenate all these vectors, right, which would give me a resultant concatenated vector, and then I could have a task specific head on top of this, and that could have predicted the yes or no class, right? The problem here is twofold. The first problem is that you already have some dummy tokens like mask, ACP, etc., right? That may impact the sentence representation. The second point is that if you concatenate them, it would be a large vector, right? Let's say if there are 10 tokens and every token is of size 512, then 512 times 10 vector, right? And then you think of the feed forward network size 512 times 2, right? Instead of that, here what's the size of this task specific head? 512 times 2, and the earlier case was 512 times 10 times 2. Now this is 512 times 2, right? The other part is that if you look at CLS token carefully, CLS token is not a part of my input at all, right? It has nothing to do with the semantics of the input. But CLS token, due to the self attention mechanism, has already attended to all the tokens. CLS tokens query has attended to all the keys. So CLS token also knows about the entire tokens of the remaining tokens some ways. Then you may say that, okay, why do I need the CLS token? The other tokens have also access to all the other tokens, right? So I could have, let's say I could have added a task specific layer here on top of I or on top of M. Why do I need this CLS? Any idea? I hope my arguments are making sense, right? Why? Now if you look at this, if you take an existing word from the input, right, it has a bias towards itself. So the query coming from I, when it attends to the key of I versus attending to the key of M, which one will be higher in terms of similarity? I with I, right? So the output that you obtain for corresponding to I, the final vector, that vector has mostly the information about the word I, right? Whereas CLS token has nothing to do with the semantics of the remaining token, so it kind of acts as a neutral token. So you see my point? By the way, these are arguments which I made in the paper. Nothing was written. Yes. You can also do the max pool. That's true. You can also do the max pool. If you do max pool, then what will happen? You essentially you end up identifying one specific vector, isn't it? Which may not be again right, because ultimately it's a sentence level prediction. You need information of the entire. You need information of both the sequences. Yeah. 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 So positional encoding is already here. No, so a batch, within a batch there's an instance. Instance has only two sentences. One is 2 sentences and the separator. No, because it's a next sentence prediction task. You should have only 2 sentences. SI, SJ.
Will be manually labeled with that.
Which part? There is nothing manually labeled here. You just sample things from documents.
How do we get to know that I plus 1 sentence?
No, you already have the document, right? You already know that this is sentence 1, sentence 2, sentence 3, sentence 4, sentence 5. You just need to write a simple code, right? And you randomly sample a pair of sentences which appear side by side, and then you basically sample negative instances. You basically take a sentence and randomly choose another sentence which not follows. You do not need any labeled data as such, right? Going to school or park, yeah. Yeah. Yes, yes, of course, of course, of course. It can be park is for mask. No, that's that. So this is wrong. So please do not assume that if I choose the word park for masking, all the instances of park will be masked. No, what you are choosing, you are not choosing a word. You are choosing a position. You are choosing 15% of 15% of positions. Think of it in this way, right? 15% of positions. Now among these 15% of positions, 80% positions you replace by mask, 10% you replace by a random token, and 10% remains the same. But I understand your query. What you are saying is that if I still give, I mean, if there is this word park, right, that may leak the information. It's not like that. So, I mean, look, our task is not to predict or to guess a specific word. Our task is to basically guess a word at a particular position. It is still difficult for the model to predict park. Okay, because think of this model before pre-training. A model is a baby, and baby doesn't know anything about the world. Nothing, no information. Okay. Of course, you can think of complex input corruption techniques, right? For example, here you just chose some chose some positions and replace them by mask. You can also think of rotating the tokens. I'll talk about it in BART and T5, right? You can also rotate. So your input is I am going to school. Sorry, your input is school I am going to, and your output should be I am going to school. Right? You can also randomly shuffle tokens. You make it more complicated. Okay. Any other question? Yes. 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 Yeah. So again, please try to understand mask language modeling. I mean, the objective of mask language modeling is to just understand the semantics within a sentence. Whereas next sentence prediction objective is to basically understand the semantics across sentences, right? So if you give a negative instance, right, and you mask some of the tokens, it would not affect the mask language prediction objective, right? It will only affect the next sentence prediction objective. Okay, these two things are different. All right, whatever I said is written here slide, so I'm just skipping. Okay, so but yeah, one important thing is to note here is so these are my token embeddings which are coming from word to wake, for example, or random initialization. These are my positional embeddings coming from sine, cosine, or rope, right? Along with this, we also need another embedding called the segment embedding, and segment corresponds to a sentence. Look at here, this is segment embedding for the first sentence, this is segment embedding for the second sentence. Positional embedding will give you the position information of tokens for the entire sequence of sentences. There are two sentences, remember this, right? You need a segment embedding, otherwise how do we know that this is a first sentence is second sentence? So this is segment embedding and then token embedding. Okay, and then you basically add all of them. Okay, some of the details of BERT. Data set was 1.25 billion words token, Wikipedia and book corpus, batch size, training time, Adam optimizer. BERT was released with two versions. The first version was 12 layer, right, with 768 hidden dimension. This is dimension of the hidden states, right, and 12 head. And BERT large 24 layers, 1024 a hidden state and 16 heads. Okay. So once the pre-training is done, then what you do, you basically teach the model different tasks, right? So after pre-training, you do fine-tuning, right? And for fine-tuning, you can take label data, for example, question answering, right? NLI, and so on and so forth, squad data, named entity recognition, and so on and so forth. And the architecture will be a bit different, by the way, a bit different here and there, but the strategies will remain the same. So pre-training and fine-tuning are two different stages. Okay, so in BART we saw different training configurations, right? Number of parameters, number of layers, and so on and so forth. We also saw mask language modeling objective, right? And once the pre-training is done, then we'll basically further fine-tune the model on different tasks, right? And the task can be question answering task, for example, squad data. I mean, if you use squad data where the paragraph in the paragraph the answers will be given. So you ask a question and the corresponding answers will be available in the paragraph. So your task will be to extract a portion from the paragraph which corresponds to the question or answer. So extractive question answering, and then named entity, NLI, and so on and so forth. So you basically adjust. Now you may not be able to use the pre-trained architecture directly for question answering and for NER, right? You need to adjust your architecture suitably for different applications, but the objective will remain the same: mask language modeling. Okay, so this is more or less about encoder model. Now in the encoder-decoder model, for example, T5, we'll discuss this briefly today. We will see that we will have a encoder layer and a decoder layer. The input will be, so let's say if it's a machine translation, so during the training time your input will be the source language, and the input to the decoder will be your destination language or target language, and at every position you try to predict the next word in your target language. Okay, and here essentially what you want to do, you want to maximize the likelihood of so basically log likelihood of y2, for example, given y1 and x. So this is conditional log likelihood, and you want to maximize this. We'll discuss this briefly. So let's look at the encoder-decoder model, right? And during the same time, two architectures were proposed. One is called BART, B-A-R-T, right? It is not BART, B-E-R-T. It's BART, B-A-R-T, bidirectional and autoregressive transformer. It's an encoder-decoder model. Okay, and at the same time, another work was proposed called T5. Okay, by Google. Okay, that is also an encoder-decoder model. Now in the encoder-decoder model, how do you pre-train the language model? How do you pre-train the language model? For example, in case of encoder model, you mask some of the tokens and you let the model predict those tokens, right? Here, how do you pre-train the model? So here, in the BART paper, they came up with this objective called input corruption, right? What is input corruption? So essentially you pot up your input and you let the model predict the actual input. Remember, this is task agnostic pre-training. So in pre-training you do not have any parallel data as such. For example, machine translation, you need a parallel data, and that's task specific fine-tuning. But for pre-training, you just have a plain text. You have raw text, free flow text, and your target is to use that free flow text for pre-training, right? So what they suggested is that so encoder-decoder model, you have this encoder layer and a decoder layer, right? So in the encoder, the input to the encoder will be the free form text, right? But with some corruption. Now what's the corruption? So corruption can be of different types. Corruption is nothing but noise, right? It can be of different types. For example, similar to mask language modeling, you can mask some of the tokens, right? So your input will be, let's say, I mask, right, going mask school. So this will be your input, and from the decoder you expect the model to predict I am going to school, and accordingly loss will be calculated and so on and so forth, right? This is very similar to mask language modeling, right? The other kind of corruption can be, let's say, sentence perturbation, right? Permutation. In sentence permutation, what you do, you essentially permute the tokens present in a sentence. I am going to school, the input will be going, I am going, I school, am, and so on, right? That's going to be your input, and your output will be I am going to school, and accordingly you calculate the loss. So these are hard tasks compared to mask language modeling. These are hard. This specific corruption is hard. Okay. It can also be rotation. For example, instead of arbitrary permutation, you can just think of rotation. For example, I am going to school. Instead of feeding this as an input, you feed in a school I am going to, right? Or if you further rotate, then to school I am going, right, and so on. And you rotate and you feed the rotated text into encoder, and you ask the model to predict. Sometimes you delete certain tokens. Remember, deleting a token and masking a token are different. Okay. So when you delete a token, let's say you delete am and to, so your input will be I going school, right? This is your input, and your output would be I am going to school. This is harder. This is harder than masking, right? Why this is harder than masking? Why this is harder than masking? Because at least in masking, you know that you at least know the length of the sentence, right? But here you don't know the length of the sentence, right? And then you can also think of text infilling. So in text infilling, what you do is you mask a span, not an individual token, right? So in token masking, you just mask a token, but in infilling, you mask a span. Let's say again, I am going to school, you mask am going, for example. So your input is I mask to school. Okay, you can think of it as back to masking, token masking, but the difference is that here you select a span, right? Now span length, how do you choose the span length? Again, you can think of a distribution. From the distribution, you choose a sample, a span length, and accordingly you corrupt your input. So they tried out different input corruption techniques, and and they feed this corrupted input, and they ask the model to predict the actual input, and that's the pre-training objective. So this is BART. So hope you understood the difference between BERT and BART, right? Encoder only, mask language modeling, and here there are different ways to corrupt the input. The first one is, so BERT is a bidirectional encoder, right? And this is an autoregressive model. Okay, and once you do this pre-training on BERT, then you further fine-tune it on tasks, right? For example, summarization can be a task where this is straightforward. Your input to the encoder will be the full text, the output from the decoder will be the summary of the text, right? And then you basically maximize the conditional likelihood, log likelihood. Around the same time, believe me, within a week of difference, both the papers came, right? And the T5 paper follows almost the same strategy that BART followed, right? With a small difference here and there. So T5, as the name suggests, this is text-to-text transformer. And the idea is that what they said is that all text-to-text or all types of tasks that you can think of, any task that you can think of, can be mapped as a text-to-text problem, right? This is difficult to digest because let's say your task is a regression problem. Let's say task is a sentence similarity measurement, right? Let's say you are given two sentences, right? This sentence and this sentence, and you ask the model to measure the similarity between this sentence between these two sentences within a scale of 0 to 5. for example. So it will generate a number, right? But what they said, that this number can also be treated as text, right? So 3.08 is nothing but 3 period 8, and all of them are characters. So any task that you can think of can be modeled as a text to text transfer model, text to text transfer. Okay, be it a regression problem, classification problem, a generation problem, everything can be treated as a text to text model, text to text transfer problem. And so you see here, for example, translate English to German, and this is the so this is the input to the encoder. T5 is an encoder-decoder model, and your output will be this. Okay, now this is another task called COLA, COLA, corpus of linguistic acceptability, corpus of linguistic acceptability, COLA task. It's a part of glue benchmark, and the task is to basically check whether the sentence is acceptable or not, right? For example, the course is jumping well, is it acceptable or not? So this is not acceptable, so the output will be non-acceptable, not acceptable. It's a classification problem. Okay, and then this sentence, STSB task, which is sentence similarity measurement, and then summary. So all sorts of tasks can be think of as text to text, and you pass it through T5, and T5 will generate the answer. And so and for pre-training, you also need to pre-train the model, right? So these are all tasks. Now when you do task specific fine tuning, then you can take data from this task and then you fine tune, but you need to do pre-training. Now for pre-training, they also adopted the same technique. They said that the span corruption technique that the BART paper used, right? The span corruption is the best technique for pre-training T5, right? So for example, your input is, thank you for inviting me to your party last week. So you identify span, a span of size 2, right here, and a span of size 1 here, and you mask it. And the difference here is that for every span corruption, you have a different mask token. In case of BERT, BERT, both cases, there was only a single token called mask, and whenever you corrupt a specific token or a span, you replace that token by mask. But here what they are saying is that at every span corruption, you replace that span by a different mask token called sentinels. Now these mask tokens are called sentinels. Okay, so number of times you mask spans, number of times, so that would be the number of sentinels that you have to include to your vocabulary. Your vocabulary size will also increase, right? Because these are tokens, normal tokens. You also need embeddings of these tokens, isn't it? For example, mask, you had an embedding. Here also we need an embedding. So what are the hyperparameters here? Hyperparameters are the size of the span, right? Where to identify the location of a span, and so on and so forth, right? And this you basically, if you follow a distribution, from the distribution you sample some number, and that number will give you the span size. So here, but I mean, there are some other differences. In case of BART, your input was the corrupted input, right? And the output was the actual input, the complete sentence, right? But here, your input is this one, thank you, mask me to your party mask week. And your output is different. Your output is this sentinel token and the corresponding span that you want to predict. Again, sentinel token, the corresponding span that you want to predict, and so on and so forth. Output is different. Now, why this output? Nobody knows, right? So, if you look at the paper, it's a huge paper. I think 60 pages paper. Okay, a lot of experiments, huge experimental setup. And Google had a GPUs and TPUs or whatever, right? So they, it's a massive experimental setup. But frankly speaking, there is no science here. I mean, this is all about empirical stuff, right? And they showed that it actually works, right? Across multiple benchmark, multiple baselines, it actually works. So what's their model? So this is their model. BERT, base size encoder decoder, right, 12 layers, and then a denoising objective, which I said, the span corruption, and the C4 data. So they collected a new data called common crawl dataset, C4 data, right? And this dataset comprises Wikipedia text, storybooks, and a whole lot of web pages, script from the internet, HTML text, and so on. And they cleaned the C4 data. The C4 data is publicly available. If you want, you can use this. And then so after pre-training using denoising objective, then they fine-tune their model on different benchmarks, right, on different tasks. So one task is this glue task, glue benchmark. In the glue benchmark, as you see, some of you know, there are different tasks. For example, COLA, corpus of linguistic acceptability, right? SST is basically a sentiment analysis task, and then paraphrase, then STSB is a sentence similarity task, QQP is a question answering task, right? QNLI, and so on and so forth. So these are standard benchmark datasets publicly available, and they fine-tuned their model on this task one by one, right? They also fine-tune their models on CNN Daily Mail dataset. This is a summarization dataset. They also use Squad data, which is a question answering data. They also use Superglue benchmark, which is another hard benchmark, harder than glue. And there are different tasks again available, and the corresponding datasets are there. So, and then they further fine-tune the model on 3 machine translation dataset: English to Dutch, English to French, English to Romanian. Okay, and what they further did, they reported their performance of the models at every timestamp, right? So every checkpoint, they reported their models performance, right? So that you can compare what happens across the checkpoints and so on. Okay, so as I said, this is a massive experimental setup. After the C4 data, they also curated another data set called MC4 data, which is a multilingual C4 data. Okay, and so on and so forth. So this was published in 2020 by Colin Raffel and their colleague from Google. All right, that's it about encoder model, encoder-decoder model, and decoder model is pretty straightforward. In the decoder-only model, you only have the decoder layer, right? Your input can be and your target is the next word prediction, right? So it's a simple autoregressive setup. You do not need to corrupt anything. You just feed your input to the decoder model, and you ask the model to predict tokens one by one, and for every token you have a conditional log likelihood value, and then you sum up the conditional log likelihood across all the tokens in the output layer, and you just try to maximize this. Okay, that's it about pre-training. If you want to know more about T5, you may again refer to want to know more means the experimental setups I haven't discussed in today's lecture. Experimental setup is huge, and I generally discuss a summary of the experimental setup, but you can refer to my previous year's lecture for that. Okay, and they showed that T5 is better than BART, right? Other encoder models, other decoder models, they had multiple experimental setups where they change the number of players, number of batch sizes, and some of the findings are non-intuitive. So those findings are used quite useful if you want to design your own models. Okay, that's it about pre-training. In the next class, we will discuss the instruction fine-tuning task. Okay, thank you.